So I've compiled the list of the 40 most missed questions by my students this year. These comprise Regents exams from 2002 to 2013. I made them using a pretty crazy spreadsheet program. If you're interested, you can go to mrhosey.com/review and check that out. I did this last year too, but for this year, these were the 40 most missed questions. You may want to look at these really quickly and see if there are any topics that you think you want to review, and you can go just to that question. I'll try to talk as little as possible and let you pause the video as needed. I encourage you as we go through these questions to read the question and then pause the video, because I will, in about 5 seconds, circle the correct answer and then go over how it is you do the problem. I also want to mention that you can get these problems at mrhosey.com/2015, or the link is in the description of the video. It was fascinating to me that 93% of people got the wrong answer to this question. And that's because most of you tried to use this formula. This isn't actually a gravity question. I mean, it is, but it's a Newton's third law question. Yes, the Earth is way bigger than the Moon, 81 times bigger. And yes, the force between them is 81 times bigger than it would be if the Moon and the Earth were the same size. But the force of the Earth on the Moon is exactly the same size as the force of the Moon on the Earth. In fact, this formula is the same no matter whether you're figuring the force on the Moon or the force on the Earth. This is like when a car hits a bug, the bug hits the car. In fact, the car feels the same force the bug does. Now, they affect it differently because they have different masses. The bug obviously accelerates more than the car does. But the force is equal but opposite. They act on different objects. A related concept is that these two forces cannot cancel out because they act on two different objects. But the answer is that the force is exactly the same. F. Problem 2. Here's the thing about angles in optics. Whether it's reflection or refraction, we're always measuring the angle relative to the normal. So anytime they give you an angle relative to the horizontal, most students get it wrong. This is 65 degrees, so this is 25 degrees for the angle of incidence and 25 degrees for the angle of reflection. Problem 3. Students hate these estimation questions, and you usually see one on question 36. One thing you can do is you can change the numbers so that they're all the same. If they're in scientific notation, you may want to change it to regular numbers. In this case, with a finger, I would change all of these to centimeters. So this is the equivalent of 100 centimeters, this is the equivalent of 1 centimeter, this is the equivalent of 10 centimeters, and this is the equivalent of 0.1 centimeters. So if your finger is about yay big, the width of the finger is about 1 centimeter. You could argue the length could be 10 centimeters. I don't know, that's a pretty big finger. But it's got to be 1 centimeter is the only one that's reasonable. While we're on the subject of estimation, some facts to tuck away. 1 Newton is about the mass of 1 apple, which is convenient. Newton, apple on head. 1 gram is about the mass of a paper clip. I should probably write that in English. In terms of height, sometimes I've seen things related to buildings. 1 story of a building, like the first floor, it's about 3 meters. Problem 4. This is a power question. Power is work over time. Now, work has 2 definitions. On the one hand, it's force times distance, and on the other hand, it's the change in the energy. So with this problem, they give you the weight force, the mg, and they give you the height, 800 meters. So you can think of that work as either the change in the energy, which is going to be mgh, or you can think of that work as the force times the distance. In either case, mg is going to be 30,000 newtons, and the distance is going to be 800 meters. And since power is work divided by time, you divide that by 480 seconds, and you're going to get 50,000 joules per second, or watts. Question 5. You have electromagnetic waves and you have mechanical waves. Sound is an example of a mechanical wave. It requires a medium. For mechanical waves, you can either vibrate perpendicular to the direction of motion, in which case that is a transverse wave, or with sound waves, they're actually compression waves. So what happens is the air tends to bunch up and then spread out, and then bunch up and then spread out. Sort of like cars in a traffic jam on a highway near New York City, if you've ever done that, where they space up and then they go really quickly and then they space up again. It's kind of like that. But the direction of the vibration in this case is in the same direction as the overall direction of motion. These particles don't actually travel east to west. They just vibrate in their place at that same point. Problem 6. Electromagnetic waves do not require a medium. There's nothing that's physically vibrating. For mechanical waves, like sound wave, there's something that has to actually vibrate. That's why you can't make sound in space. There's nothing to vibrate. So they don't require a medium for electromagnetic waves. Electromagnetic waves are transverse wave, actually two transverse waves, an electric field and a magnetic field. I will attempt to draw that poorly. This coming in another plane. That's actually not bad. But you don't need that to answer this question. In this question, sound waves are longitudinal waves. E&M waves are transverse waves. E&M waves don't require a medium. Mechanical waves, like sound, do require a medium. However, they do both vibrate at the same frequency as their source. Question 7. There's this really weird thing that happens. Matter, at least when it's small enough, actually behaves like a light wave or a light photon and can do wavy kind of things, like diffraction, for example. If you were to fire electrons through a small enough slit, you would find that they would actually start to spread out kind of like that. And they would interfere with one another if you had multiple slits. And you can do cool things like look at viruses with a scanning tunneling electron microscope or something like that. I'm no expert. But if it's small enough, matter, such as electrons, actually does behave like a wave. And the best choice here is definitely electron diffraction. Question 8. By telling us that the temperature is constant, that tells us that the resistance is constant. One thing you do need to know in Regents physics is that as the temperature gets warmer, the resistance generally gets higher, but here that's being fixed, so the R is not changing. So that means if you make the voltage go up, the current has to go up. It's like using a bigger battery is going to give you more current just the way it always does. But the fact that they throw temperature in here is going to throw some students off the scent. Question 9. This smells like a vector question, and it is, but not in the way most students are going to assume. Most students see two numbers here, and they assume that you're going to have to add those numbers like vectors, because we do that so often. This isn't that question. What you have is you have a river, and there's something floating, and the water is moving down this way at 1.5 meters per second, but their toy is moving across the river at 2 meters per second. And if the question asked what the resultant was, you would add those by the Pythagorean theorem. But this is not that question. This is asking you to understand the independence of the x and y components. So no matter how fast the river is flowing south, the boat is still going to be moving towards the shore at 2 meters per second. So if we want to know how much time it's going to take to move across, you're just going to take that distance across the river divided by the velocity, but only the velocity in the x direction. So you're going to take that distance 30 meters and you're going to divide it by 2 meters per second, which is going to give you 15 seconds to go across the river, no matter how fast that water's flowing. Now the total distance traveled does depend on the 1.5 meters per second. If you had a river going at 100 miles an hour, it would go pretty far in those 15 seconds, but it would still take only 15 seconds to go across. The x and y components are completely independent of one another. Question 10. This question says, mix up sound and light. They're different things. If you have a light wave go from water to air, it's going to speed up. In fact, in air, it travels almost the same speed as it does in a vacuum. But this isn't light. This is sound. Sound is a mechanical wave. It needs a physical medium. In fact, generally speaking, the more densely packed molecules or atoms are, the faster the sound wave is going to travel. So sound tends to travel fastest in solids, pretty fast in water, and slowest in air. Even if you were to think about this purely in terms of numbers, if you look on the reference table, they give you the speed of sound in a vacuum and the speed of sound in air. Notice these two sounds are very different. While we're on the subject, there's been a recent trend on the exam to ask about something called order of magnitude. If someone was to ask you how many orders of magnitude faster is light in a vacuum than sound in air, what you would do is you would look at these two numbers and you would completely ignore the first part. And you would pay attention just to the power of 10. So that's an 8, that's a 2. What we would say is we would say that light is 6 orders of magnitude faster than sound. So just one of those things. I don't know if they're going to ask it again, but it's something that's been a little bit different you may want to pay attention to. What you don't want to say is you don't want to say that it is 10 to the 6th orders of magnitude. That would actually be wrong. That would be like a 1 followed by a million times faster orders, which 6 orders of magnitude. Physics teacher has been talking about that one a lot. Question 11. The Regents doesn't ask a ton about magnetism, but when they do, one of the popular questions is what would a bar magnet do? So you can think of a bar magnet having a north end and a south end. And magnetic field lines are going to tend to point in the direction that a north pole would want to go. So this would sort of push the North Pole in that direction, much like a weather vane in the wind, something like that. It is worth noting that as far as we know, as far as I know, you can't actually have just the north like you can with electric charges, but they don't seem to ask about that. Another question that comes up from time to time is using a bar magnet, how could you quote-unquote make electricity or generate a voltage? If you see a question like that, if you take a loop of wire like this, and you take a bar magnet and you move it through the loop so that it changes the magnetic field going through that loop, it will generate a voltage. So that's something to keep in mind. Question 12. This is the same concept as earlier. If you have a wave that's propagating east to west, but the individual particles are vibrating north and south perpendicularly, that's the definition of a transverse wave. If they had been vibrating this way, that would have been a longitudinal wave. But this is a transverse wave. Question 13. There was a time when the Regents loved to ask this question. Which object has the most inertia is equivalent to asking which object has the most mass. That's it. The velocity doesn't matter. If they were asking which has the most momentum, that would be the m times the v. So choice C would have the most momentum, but the choice with the most inertia is choice D. Question 14. This is an energy question. The energy at the top of the ramp should be the same as the energy at the bottom of the ramp if there's no non-conservative forces such as friction to take energy away from the system. So if we figure out the potential energy at the top there using mgh, well, mg is 40 newtons and h is 8 meters, so that means at the top of the ramp you have a total energy of 320 joules. If the block loses 50 joules of heat, it goes into Q, into internal energy here. That means that you have remaining 320 minus 50, 270 joules of energy. Now you'll also see this sometimes, for example, with a pulley, and a person might put in 300 joules, but then when you do the MGH and the block going up, it has less joules. That difference went into internal energy. Friction took heat away, warmed up the pulley, maybe made some noise, made some squeaky, but the energy left the system. Question 15. Very common misconception. If you have a radio wave, people think like radios in your car. People still listen to those. And you think of music. And music, you think of sound. Sound travels at 331 meters per second in air. We're talking about radio waves. We're talking about a type of electromagnetic waves, basically a different flavor of light. So it's going to travel at the speed of light in a vacuum. So even though they're radio waves, they're still electromagnetic waves. They're not actually sound waves. There's no physical matter vibrating. Question 16. This is a friction question. The fact that it's moving does tell us that it is kinetic friction. Remember, you have static friction and kinetic. Static is usually bigger. But the actual velocity doesn't matter. What you need to do is you need to take the coefficient of friction, which is 0.67 for rubber on asphalt, times the normal force. By the way, mu, coefficient of friction, is one of the few things, along with n, in the course that don't have units. It's a ratio of two things. In this case, the force applied to or the friction force to the normal force. And the normal force, which for a block, generally, if it's on a flat surface, is equal to its weight force, in this case, 60 newtons. So 2/3 of 60 newtons is 40 newtons. That is the answer. Question 17. V equals F lambda, 331 meters per second for sound in air. The given frequency, 512 hertz. Lambda. So lambda is going to be 0.646 meters. As long as we're on the subject, now I don't know why you wouldn't know that lambda's in meters, but let's say you were fuzzy on what the unit was for the variable. You actually could write this as 0.646 meters per second over hertz, and that would be fine. So if you're on a B2 or C and you're uncertain of the final unit, use the units that you substitute in and put that on the final answer, and you will receive full credit. Question 18. So there's a longer way most people will solve this, and there's a pretty slick mathematical reasoning way that I hope my students will use for this. First thing you would do is you would find the mass of an object at a known distance, meaning you know the distance here, and you know the force. So you can plug in 1,000 newtons, that should say 1,000 newtons. The distance, 6.37 times 10 to the 6. Plug it in, you'll get a mass of 101.7. By the way, some of you may have noticed that's the radius of the Earth, so 1,000 newtons would be about 100 kilograms, but that's just for fun. If you plugged it in, you'd get 101.7 kilograms. Then what you would do is you would use the same formula for the gravitational force and plug in, now that you know the mass, 101.7, and you're given the force 28 newtons over r squared. And you got to be a little bit careful with the squaring. I recommend putting in the numbers with your calculator using that second E button. But if you do that carefully, you should get this number. Now, the slick way to do this is to recognize that the only thing that we're changing here is the distance and the force. So what I like to teach my students is to pretend that every other variable is just 1 because it's not changing between the two scenarios. So we end up with 1 over the distance squared. Since we're solving for the r, we're saying that r is proportional to 1 over the square root of f. Meaning the factor by which f changes will tell you the factor by which r changes. So if we plug that in, that's 1 over, well, we want to know 28 newtons, and before it was 1,000 newtons. When you take the square root of that, what you get is 5.98, meaning you have to be 5.98 times further away than you were when the force was 1,000 newtons, so that the force will be 28 newtons. So if you take 5.98 times 6.37 times 10 to the 6th, you will get 3.8 times 10 to the 8th meters. I mean times 10 to the 7. Whoops. It happens. So 5.98 times 6.37 times 10 to the 6th equals 3.8 times 10 to the 7th meters. That was a hard one, but it's a good question. Question 19. Again, we talked earlier, when the temperature decreases, the resistance should decrease. So the resistance of this resistor is decreasing. In series, resistances add, so that means our total is decreasing. And then by Ohm's law, when the resistance decreases, the current in that circuit is going to increase. What I would do for this lamp is look at the power of the lamp, because the brighter it is, that means it's using energy at a higher rate, more power. I would look at I squared R. So that means as the I increases, it's going to increase more than the resistance is going to decrease, which is going to increase the power. Another way to look at this is that these 10 volts from the battery must be quote-unquote used up. That energy's got to be used as the current goes through the light bulb and through the resistor. If this resistance goes down, that means less volts are going to be used up here, which means more volts are going to be used by this light bulb. So then if you look at this equation, if you have a higher voltage and the same resistance, that's going to be more power. So no matter which way you look at it, as the resistance of the nichrome goes down, the energy used by the lamp per second is going to go up. Question 20. Remember, diffraction is a wave phenomenon where the wave spreads out as it passes through a slit or a hole, and what matters is the relative size of the slit in the hole. So the smaller the slit, the more the diffraction, the more bent, like on the left, and the bigger the slit, like on the right, the less diffraction. If it's a really big slit, it passes right through. Like there's almost no diffraction when you shine a light wave through a doorway, but there is diffraction for a sound wave through a doorway because they're closer to the same size. Problem 21. Problems without numbers tend to drive students a little batty, but this is a good one. It's conservation of momentum. And whenever you have a conservation of momentum problem, what you do is you take the momentum of the system before and set it equal to the momentum of the system after. Each thing in the problem has its own momentum. Now in the beginning, the big block's not moving, so the momentum before is just the momentum of the, I guess that looks like a bullet, little m times its v. Afterwards, you have one object essentially that is that big block plus the little block. Little block plus big block. And it has some new velocity after, which I'll call v prime. So when you divide, you get that v prime equals little m over little m plus big M v prime. But it all starts with the conservation momentum. The momentum of the pieces before, when you add them all up, has to equal to the momentum of the pieces after. Worth noting, sometimes you can also have what's called an elastic collision. And an elastic collision, it's going to look more like m1v1 plus m2v2 is going to equal m1v1 prime plus m2v2 prime. Notice it's just the pieces of momentum, you add them up before and after. Problem 22. This is the equation everybody loves. And when you plug it in, you have to remember that the mass has to be in kilograms and the energy will be in joules. In this case, you're given it that way, so it's not a problem, but 2 times 10 to the negative 5th kilograms, and the velocity is 3 times 10 to the 8th meters per second. But don't forget to square that. And when you do that, you wind up getting 1.8 times 10 to the 12 joules. That's a big number, so we have a prefix for it. Don't forget about the front page of the reference table. Has prefixes. That's a tera, so that's 1.8 terajoules. Problem 23. This is a question about the difference between weight and mass. They ask specifically about the mass. When you go to a different planet, your mass does not change. How hard gravity pulls on you does, but the amount of mass doesn't. If you were to bring a balance to that new planet, you would find that your mass would be the same. Compared to 1 kilogram, you would be the same number of times more massive than that. However, if you bring a bathroom scale, which measures force, you would be pulled less hard into that bathroom scale because the planet is a different mass itself and pulls a different amount. I always like to say that if you want to lose mass, go to the gym. If you want to lose weight, go to the moon. Although it's funnier when you say it the other way around. By the way, for those of you who picked choice D, that would be your weight on Mars. 3.71 divided by 9.8 is 37.8%. 37.8% of 19.6 newtons is 7.42 newtons. That's an example that I like to call giving the right answer to the wrong question. If they were asking about the weight on Mars, you'd have been golden. But they didn't. They asked about the mass. So you just have to be really careful when you read. Question 24. This is a superposition question. Both of these pulses can live in the medium at the same time. To put some numbers to this, let's say this was blue and this was green, although those are colors. Let's say this was +1, and let's say that this green was -3. When they're in the same medium at the same time, -3 plus -2 is going to give you a net that is -2. So that's how you answer that one. Worth noting, interference, as this is called, superposition's the adding. Interference, what you get, can be constructive if it's bigger, destructive if it's smaller, and those can be complete or incomplete. But as far as drawing it, you just mentally add them like this. Question 25. So when light travels in different mediums, it travels at different speeds. How fast that is depends on this. So N equals C over V. You're given that N for Lucite. Well, you're told it's Lucite, so you look it up in the reference table. It's 1.5. So if 1.5 equals C, which is 3 times 10 to the 8th meters per second, over the mystery velocity in Lucite, that velocity is 2/3 of what it would be in a vacuum, and that is 2 times 10 to the 8th meters per second. So still pretty fast, but slower. To get the wavelength from the frequency, you use V equals F lambda. V equals F lambda. Now you use 2 times 10 to the 8th meters per second, and you set that equal to 5.09 times 10 to the 14th hertz from the problem. Lambda, and you're going to get a wavelength that is 3.93 times 10 to the negative 7 meters, which is the answer. Once in a while you see nanometers, which is 10 to the negative 9. That would also be 393 nanometers, but the choice is A. Question 26. Generally, this is a case of overthinking it. They gave you the frequency, so to get the period is 1 over frequency. The period's 1/60th of a second, or choice A. Question 27. There are two things going on as the car pulls away from the observer. On the one hand, it's getting farther away, so it is getting a little bit quieter. The amplitude is decreasing. It's not getting louder as you get farther away. The second thing that's coming or going on is, if this is the observer, and let's say that this car is producing 500 hertz frequency. In between cycles, the car has now moved somewhat farther away. So each successive pulse has a little bit farther to travel. That results in the person that's listening hearing a slightly lower frequency. So this person might hear, for example, 510 hertz. The faster you go, the bigger that difference in frequency is. This is called the Doppler effect. If a car was to be coming towards you, you would actually hear... whoops, I have that backwards. I'm not going to delete a whole video because I made a mistake, but as the car's moving away, you're going to hear a lower frequency because each pulse travels a bigger distance. If the car was traveling towards you, you would hear a higher frequency, and the faster it moves, the bigger the difference. With sound waves, you hear that as a higher pitch coming towards you and a lower pitch as it goes away. With light, they call it the red shift and blue shift. As a star, for example, moves away from you at a very fast rate, it's still shifted so that it's a lower frequency, but that lower frequency we call red shift because red is a lower frequency than blue. And as a star comes towards you, that higher frequency, we call it a blue shift. It doesn't necessarily look red or blue, but in fact it doesn't usually, but it's going to shift it in that direction. But the answer is A. 28. This is called wave-particle duality. Light acts as both a particle and a wave, and particles, when they're small enough, can actually act as a wave or particle. So an example of electrons acting like waves that we've already talked about was electron diffraction. So if you pass electrons through a small enough slit, they can spread out, diffract, interfere. It's pretty fascinating. And of course, electrons can act like particles. An example of photons acting like particles would be the photoelectric effect, where light wave or a photon hits a metal and has enough energy that it ejects an electron. That's the photoelectric effect. And of course, light can behave like a wave and do wave things like diffraction. But it's this concept of wave-particle duality, and it applies to both photons, particles of light, and it applies to very small particles like electrons. Question 29. Once again, sound waves are mechanical waves that are longitudinal. The vibration is in the same orientation as the direction of propagation, even though the material doesn't actually move. So air vibrates in place, and that wave is propagated in the same direction as the vibration. Question 30. We talked about this back on question 20. The bigger the wavelength is compared to the slit size, in other words, the ratio of lambda to d, the more diffraction. So on the left, small slit, more diffraction. On the right, big slit, less diffraction. But the answer is C. Question 31. Remember, photons can only be absorbed by an atom or emitted if the electron jumps between two discrete energy levels. The problem is if an electron's in the ground state, it needs this much energy. 13.6 minus 3.4 is 10.2 electron volts. So we can say definitively a 9.4 electron volt photon can't be absorbed because it's not even enough energy to get from the ground state to the second state. So the photon's energy is too small. Question 32. You have maximum constructive interference when the wavelengths, or when the waves are a whole wavelength out of phase, or 0 wavelengths, or 2, or 3, etc. You have the most destructive interference when the wavelengths are half a wavelength, or 1.5, or 2.5 wavelengths. A way of referring to this difference is also in terms of degrees, where one full cycle, one wave, is 360 degrees. So 0 degrees represents 0 wavelengths out of phase, 90 degrees represents a quarter, and 180 is a half, 3/4, etc. So 180 degrees out of phase would be completely destructive. 0 degrees is completely constructive, so that's the answer. Question 33. Don't forget about these electrical power equations. In this particular problem, if P equals V squared over R, then R is simply V squared over P. You're given 4.5 volts, and you're given 1950 joules, and that's going to give you an R that is 37.4 ohms. Question 34. Power is work divided by time. Work is power times time. It's electrical. Use work equals VI times T. Question 35. Units for work. Well, work equals force times displacement. Now, you're not calculating the work this way necessarily, but recall that F net equals MA, which means the units for force are the same as the units of mass, kilograms, times the units of acceleration, meters per second squared. And of course, the units for distance are meters. When you multiply these two things together, you get kilogram meters squared per second squared. Question 36. One word changes this question completely. Net. The net force acting on the metal disc is actually 0. Yes, you have a weight force that happens to be 1 Newton, but you also have a normal force that equals 1 Newton. And the way I know that is that the metal disc isn't accelerating. It's not going up, it's not going down, it's at rest. So therefore, the net force has to be 0. The fact that the acceleration equals 0 tells us that the net force is 0. In fact, in class, I have this little thing I do where when the velocity is constant, say you're in a car merging on a highway, and you reach that moment where you're going at a constant velocity, say 60 miles an hour, to think about how miraculous that is. And that all of these forces from all these collisions with all these little air molecules, you know that the net force is 0. How do you know that? Just by virtue of the fact that you're going in a straight line at a constant velocity. So I throw my hands up in the air and I say, Eureka, we've done it. We've balanced the forces. Net force is 0. Constant velocity in a straight line. It's even more fun than it sounds like. Question 37. Sorry, it's so small. This is a Newton's second law question, F net equals ma. They tell you that the cart is slowing down and that it's moving to the right. So if it's moving to the right, but it's slowing down, its acceleration is to the left. which means its net force must also be to the left. In fact, it'll just be MA. So we're looking for the car where their net force is to the left. So when you look at this first question, it can't be that because the F net is to the right. If you look at the second question, F net is to the left. So that's actually going to be our answer. When you look at C, F net is 0. That's constant velocity. Eureka, we've done it, but that's not the answer to this question. And the same thing here. Net force is 0. So the answer is B, where the net force is to the left because the acceleration is to the left. Question 38. The definition of electric potential is the work to move a coulomb of charge between two plates or two places where you know the potential. So here you're told that it's 36 volts. That's the V. And you're told an amount of charge 4. Now microcoulomb, anytime you have micro, it's times 10 to the negative 6. So if you want to know how much energy there is, work is just going to be QV, which is 4, in this case times 10 to the negative 6 volts. I'm sorry, coulombs. Times 36 volts. And that is going to give us our answer. 1.44 times 10 to the negative 4. Question 39. When it comes to springs, there's two things to consider. One is the force, and the other is the energy stored in it. So if you have a spring and that's its natural rest length, and you pull it, and let's say it stretches some distance x from rest, the force required is kx, where k again is a spring constant, number of newtons per meter that you want to stretch the spring. There's also energy that's stored in that spring, given by 1/2 kx squared. You stretch it twice as far, it stores 4 times as much energy. This is a straightforward plug-it-in problem. 1/2 times 30 newtons per meter times 0.5 meters squared gives you an energy of 3.75 joules stored in the spring. So now, as promised, I put up for you the answers to all of these questions. Let's probably move that over. So for all, there's actually only 39. The 40th question was just a typo, so I just left it off. C'est la vie. But if you want these questions, to do them, if you go to mrhosey.com/2015, or if you want last year's, go to mrhosey.com/2014. Also, a program I use to kind of make this, and it's a pretty slick review program I made in Excel. I'm having some of my students use that. If you want to try it, you can go to mrhosey.com/review, and there's a video that explains all about it. I showed a screenshot in the beginning, but I managed to keep it much shorter than last year. Hopefully somebody somewhere finds this helpful. Good luck on the exam, and just remember to make sure you're always answering the question that it's asking. It's more painful to give the right answer to the wrong question than it is to actually just get it wrong. So just be careful, go slow, you'll be fine. I hope.